Well, thank you very much, everybody. My name is Gabriel Weymouth, as Bernard said. Thank you very much for the invitation and the intro. I had a little bit of last-second excitement as my docking station went completely AWOL this morning and broke. So I was hoping to get some demos going, but I'm not sure this is the right moment for it, unfortunately. Luckily, we have lots of videos, and one of the best things about the stuff I'm going to talk about today is that it's super user-friendly for everybody. So even if I don't manage to give a demo, you guys can. You can go use it yourself. So the theme of the talk today is moving towards accurate real-time simulations of unsteady nonlinear fluid structure interactions. This has been a goal of mine for a very long time, since my PhD, as Bernard mentioned. And there's a lot of things I could talk about on this, but since this is for a supercomputing facility, and I was told that people would like some more of the kind of implementation details, I thought I'd dig in a little bit to the meat that's underlying some of these solvers that we've been developing for the last decade. And kind of a consistent theme with that is this idea of pressure. So trying to get the incompressible part of these simulations working correctly is not trivial, and it requires a lot of special care. So it puts pressure on you as a person, and you need to get the pressures right as an engineer as well. So here's a few examples of places where we're interested in getting real forces and real flows. We can't just have pretty pictures if we're trying to solve real problems. And a lot of these are problems that we don't exactly know how to solve already. So if we're just talking about, so I work in the Marine and Maritime group here, but the most important thing in kind of moving forward in the maritime field is to lead and try to deal with things like climate crisis. And so looking at things like wind turbines and also kites on a ship here. I should give myself a little cursor. Laser pointer, there we go. So this is a kite that's been added onto this ship, but we don't really know how to design kites for ships. You may be surprised. So there's a lot of really interesting questions here. Fluid structure interactions questions, control questions, all kinds of stuff. Another thing here, this is a military naval application. So this is a stealth ship. And when you're trying to be kind of radar invisible, it means that you need to have a different cross-section than a normal ship. And you need to make sure that all of your methodologies keep working, despite the fact that you've changed something fundamental. And then there's also kind of autonomous underwater vehicles. These are a lot newer, and as we move forward in what we want these to be able to do, then they have kind of new designs and challenges as well. So this is the AutoSub, better known as Boaty McBoatface, which is a cool design, and it's a great vehicle for going straight. But what if you wanted to be able to kind of get up close to a coral reef and maybe give it some medicine or something? So that needs something that doesn't look like a torpedo. It needs a very different design. So we've got a lot of new challenges. There's also players outside of engineering who are really interested in CFD and computational fluid dynamics. So biology, paleontology, sports science. These groups are all really interested in using better technologies. And it can be tricky because there's a big learning curve typically with these kind of things. And also these flows are incredibly unsteady. All of these kind of geometries are deforming and changing shape, almost fluid themselves. So we need some kind of technology that can handle stuff like this. Unfortunately, the kind of ideas that we used in classical fluid mechanics and classical ship design, they don't translate particularly well as we move to these more unconventional forms. So this is a cool example. Boats are prehistoric, actually, literally prehistoric. They show up in the first records. And hydrodynamics is quite old. So this is Bernoulli's text that introduced hydrodynamics, which is nearly 300 years old now. But even as recently as less than 100 years ago, when somebody was trying to estimate the forces induced by a dolphin, that's Sir James Gray, he misestimated by an order of magnitude to the point where he couldn't understand. It seemed to him as though it should only be producing 10% of the force that it actually does. So kind of your back of the envelope armchair estimate isn't sufficient. We need something that can give us quantitative results and do so very, very, very fast. So this is all motivation to try to give the idea that kind of live simulations are what we really want in this case. The armchair estimate is appealing because you can immediately start thinking about, what if I changed this factor? It's the same reason why analytics are great in general. And if you have to send stuff off to a supercomputer cluster for 2 months before you get the answer back, you've just cut down your creativity by a huge margin. So we've been working on some tools for that. Like I said, this is a jellyfish simulation. I was going to try to run this live, but like I said, my computer isn't very happy with me about it. Oh, one little guy. Apparently it's so not happy with me. Okay, there we go. So this is a jellyfish simulation. It's deforming geometry. It is a viscous flow simulation. It's accurate, and unfortunately, I can't show you the demo right now, but this does run live on my laptop. I set up this demo for my professor inauguration a couple of weeks ago and ran it live with no problems whatsoever. And on that previous slide, I showed you how long it took me to set up this demo. So this is the code that sets up that jellyfish demo. This is it, literally, it's 10 lines of code within this function that defines that simulation. And this is the kind of quick kind of prototyping that then leads to an immediate real-time on your laptop run that gives you quantitative feedback, so you're not off by an order of magnitude. It also really helps you foster understanding. So the previous version of this stuff was all 2D, called LilyPad. And I would use this example when teaching all the time. So teaching lifting line theory is great, and something that we do, of course, in class to help understand the basics. But you also want to show that as we increase the angle of attack too far, so I can kind of do that by controlling some of these sliders interactively in class, that I get leading edge separation and I get a big wake and my drag force gets enormous. So this is the kind of stall phenomena. And instead of just waving my hands or showing an old video, I can do this interactively. I can give the tool to students and they can do it interactively. Even better, Christina van der Waal in the University of Southampton used LilyPad to set up this cyber physical experiment. Because LilyPad runs in real time, she can just put it in the loop for an experiment. So this box here is full of water, and there's an inlet and an outlet, which is moving the water through. And this little black guy here is a camera that looks down and figures out where these blocks are. And this is great for younger kids. They can grab these blocks and move them around, and they can look at the screen and see what that does to the flow in real time. So they can move one block in front of the other and see that there's kind of, a wake that they can go inside. And you can talk to them about how this is birds fly and it's cyclists drafting behind each other. And this stuff is just wonderful for education, not just for students, but also for researchers and professors. Everybody needs tools like this, and they're really, really helpful. All right, so that's the goal. So that's the goal, but the problem here is, that's a great ambition, but how does this actually work? So what I want to talk about for the rest of my time is 3 kind of levels of diving in on how to accelerate this incompressible solver. This is an example kind of application that an old PhD student, Andini, made and published some related work. So this is kind of the anti-Sir James Gray, right? We're actually doing these simulations. But how does this work? How do we put in some geometry and then we get out accurate forces? All right, so the first thing I want to talk about is that we made a choice a long time ago in my PhD that we try to move in this direction through Cartesian-grid methods. This is an algorithm design choice, and it's not the only way to do it, but it does have a number of advantages that are worth mentioning. The first is that it's trivial for computers, for developers, and for users. It just makes everything so much easier. So for the computer can be very happy because you just store all the data as an array. Everything's continuous, everything is nearby, things in space are close together in memory. It's wonderful. Of course, as the developer, it's great too, because if you can just take a derivative by taking the difference between two nearby points, that simplifies all of your algorithms, right? And we'll talk a lot more about algorithms in a second. And kind of the most important thing for the user is that it gets rid of grid design. And to be honest, grid design is fundamentally unnecessary. It's just a numerical baggage that's put on top of what the people actually want, which is to understand the fluid mechanics of what's going on. It's definitely the primary source of user error and the most annoying learning curve when you're trying to teach people how to use some code. And that gets rid of all of that. So I think that's probably the biggest advantage of all. Talking about the numerical advantages and the algorithms a little bit more. First of all, I really think that Cartesian grid methods can be more accurate than fitted grid methods. They definitely are more accurate in some cases. So we're guaranteed to have accurate and perfectly conservative fluxes because our geometry is trivial. There's no limitations on the boundary topologies that we have to worry about. I don't have to worry about cells intersecting or becoming improperly skewed. None of that ever happens. It's impossible. And of course, because this thing is very simple in terms of the computer, just an array, it's very low cost, very low memory, and that means we can scale up our degrees of freedom, even on a simple thing like the laptop that I'm running on here. So that increases your accuracy too. And I'll talk more about the fact that we can use a geometric multi-grid pressure solver, which is a very accurate and fast way to solve these kind of problems. So I think Cartesian grids have kind of been the agreed upon solution for difficult two-phase flow simulations for quite some time. The volume of fluid method and the, no, not LES, well, yeah, the volume of fluid method is a very good way to do two-phase flow simulations. But the big yellow box there has to be done too. So this is the flow past a ship kind of model, and we're looking at the rooster tail behind it. And nobody bats an eye about trying to use Cartesian grids to deal with these very complicated structures because there's just no other way to do it. But the truth is there's a lot of inaccuracies in VOF. Before my PhD, there wasn't even a fully conservative 3D method. So I think it's important that the kind of stigma, maybe a little bit, on immersed boundary methods for solid boundaries is addressed. So let's talk about that a little bit by explaining what the method is that we're using for these cases. That's not really supposed to be animated. Okay, anyway, so the situation we have in all of these cases is that we have two domains. We have a fluid domain, omega F, and we have a body domain, omega B. And there's some boundary between those two. And we have the governing equations in each of those domains. The governing equation in the body domain is easy. It's just that we kind of want to set the velocity inside the body to match the body velocity, which I'm using capital B for here, B for. So we'll drive those two to zero. So this body equation. The fluid equation isn't that complicated either in a sense. It's the Navier-Stokes equation. I've integrated the equation so that it's an update equation. So we're saying that the velocity at any time minus the velocity at some previous time is just this integral. So this is the Navier-Stokes equation, the convection term, the pressure term, and the viscous term of that equation. And this also should be zero, right? And these are true in their two domains. So velocity is given by this update equation in the fluid domain, and it's given by the body equation in the body domain. this problem isn't that hard to solve. There's a lot of fast methods to solve the Navier-Stokes equations. People have been doing it for a long time. Again, using Cartesian-grid methods. So they're fast, they're accurate, no problem. The issue that we come up with is when we try to put these two things together. Oh, I'm missing an animation. But the issue is when we move these two things together and we try to combine it all into one package, is that we end up with irregular data. So we have a mix between these two. Our domain is irregular and our data type is irregular. So the boundary data immersion method is the approach I developed. There's other kinds of Cartesian grid approaches, but I'll explain this one because it's the one that we've been using. And the idea is that we convolve those two equations so that you get a meta equation with regular boundary data. So instead of going into a fitted grid method, kind of throwing out all of the advantages of the fluid subproblem on Cartesian grids, or doing cut cell methods or things like that, where we're sort of approximating fitted grid methods, we'll just change the governing equation a little bit. So we'll take that governing equation we had and we'll integrate it over a kernel. So this is some little kernel function, and at any point, we'll integrate over whatever their local equations are. And there'll be some width to that integration, epsilon. These two things then, since I've integrated over this kernel, now they apply over the full domain. And I can just add the two equations together to get a single equation, which is valid everywhere over the complete domain. And that'll generally ramp between these two governing equations in one type or another. So when we're totally out of the body, then we'll get the fluid equations recovered. When we're totally inside, we'll get the body equations recovered. And in the middle, we'll get some kind of new equation, this meta equation. We can look at that in a little more detail. So those two kernels here, this would be pretty complicated and expensive to compute directly. So this is the Navier-Stokes equation, right? So multiplying that by a kernel is expensive. But we can cheat a little bit. We can just take the moments of the kernel, and then they pull out of that integral, and we end up with just the 0th moment of the kernel times the fluid equation, and the 1 minus the 0 moment times the body equation, and then a second term here, which is related to the first moment. This first term in blue, this is blending the two domain equations together. So it's just a smooth ramp function, right? Where this one is 1, then I just am left with f. These two cancel, b is gone. When this is 0, this term's gone, and this is 1. So we can see exactly that it gives us that kind of two-domain approach. The second term, which was developed by Audrey Martins and her PhD, this is really important when you're dealing near the wall, for near wall discontinuities. So this is something which a lot of immersed boundaries aren't taking advantage of. So here's a quantitative example of that. This is the flow past a very thin foil at a relatively high Reynolds number. And there's separated flow here. And this is the body fitted grid solution. This dashed line is indicating the reversed flow region. And we can see that with our second order beat-in, with that kind of second moment of that kernel, we're reproducing that extremely accurately. Whereas the first order, the discontinuity is being smeared out, and we don't want that. We want a nice tight boundary layer. That's very important. The discontinuity, of course, is in the velocity derivative, but that shows up in the momentum equation. There's a velocity derivative, so you can't smooth that out. We can be more quantitative. I like pretty pictures, but we can get quantitative too. Here's the surface pressure coefficient on the top and the bottom. Again, the body fitted and the second order beat-in are essentially exactly on top of each other. Direct forcing methods or first order beat-in don't handle this kind of complicated case very well. We can get the surface forces as well. But let's think about the pressure a little bit more, like I was indicating before. A very nice Twitter user just a couple hours ago asked a question, which is perfect for me to jump on top of. He says, amazing results. One question, how do you handle grid points inside the solid with 0 coefficient for the Poisson equation? That seems like it would lead to an ill-conditioned mason. Well, thank you very much, Hamdi. I'm happy to answer your question. Maren Lauber is a former PhD student as well. He's been working on this and has a couple cool papers that really dig into the pressure solver side of this thing. So consider the pressure on a thin flexible sheet. I think this is kind of the worst case scenario for immersed boundaries because the pressure is really tightly coupled to the structure, obviously. Any motion of the body is generating the pressure derivative. So this is the normal component. If there's any acceleration of the body in the normal direction, that changes your pressure derivative. And of course, whatever the pressure derivative is across this geometry, that's a video too. Oh, so sad. Please click. Oh, that's such a pretty video. How do I get rid of the laser pointer? Oh, well. Sorry, folks. So this is a dynamic geometry moving back and forth in a very pretty way. And when it moves back and forth, it changes the pressure. And of course, the pressure also changes the flow. And the pressure is discontinuous across this boundary, in addition to the tangential velocity, like we talked about before. So how do we handle that? The real trick is that the velocity projection and the boundary conditions can't conflict. If these two things conflict, then you're going to have a very, very inaccurate flow. So if you don't really do the velocity projection step, if you do artificial compressibility or any other kind of trickery, lattice-Boltzmann methods, you're really going to kill your pressure forces. They're not going to be accurate at all. The dynamics will be terrible. So you can't do that. You can't skip the pressure solver. Similarly, though, unfortunately, even if you do the projection, if you do some kind of a projection that violates the boundary condition, so that now we're getting velocities that don't match the body velocity, that's just as bad because it means you've solved for the wrong pressure. So that kills the pressure and the forces. And you really can't ignore that when you're doing the immersed boundary force. All right. So this is a really cool example from Marin's paper in 2022, just last year, that really illustrates this extremely well. So the setup here, man, none of my animations are working. That's so sad. Oh, well. So the setup here is that we've got a pipe, which is arranged in a ring. So here's our domain. And on one side, this flows right into the other side. So you can imagine the pipe just bent together end to end. And inside there, you have a little piston, okay? And the initial condition is that everything's static. Nothing's moving, the piston's just sitting there. We've got a 1D incompressible flow, and we're not going to consider any kind of friction forces. And so this gives you a really simple momentum equation. You've just got the next velocity is going to be some function of your pressure. So this is just a little scaled pressure. So it's pressure scaled by dt over rho. So this velocity is going to be minus the gradient of your pressure term, plus whatever kind of immersed boundary forcing you use. So in this case, I've indicated what the immersed boundary forcing looks like. What's interesting and really great about this case is that as soon as we start moving the piston, we know what the solution needs to be. The velocity everywhere needs to match that body velocity because we have a 1D incompressible flow. There's no other possible solution. As soon as the boundary condition says that the velocity is not zero here, then throughout the entire rest of the flow, we also need to be not zero. So that's our bottom picture here. As soon as this starts moving, the whole rest of the flow needs to be moving as well instantly. That's the job. But how are we going to do that? Look at this equation. Our next velocity step, the forcing on that can't extend to the entire domain. It's an immersed boundary method. Our forcing needs to be local to this piston. So here I've kind of indicated that by saying we've got some sort of a delta function, or in terms of the previous slide, it's like 1 minus the first moment of the kernel. And the force has to be totally local to this. It can't extend all the way through. So how can this work? How can we get the correct velocity we want where we're not allowed to change the forcing everywhere in the flow? So what BDIM does, what has to happen, is that the forcing needs to include the pressure term. If it doesn't include the pressure term, there's no way to solve this simple problem. So the forcing that we need to use it's got to include something related to the velocity, but also the pressure. So writing it a little bit more, just substituting it, this is our BDIM version of the governing equation. We get 1 minus this delta function near the body, and we get the forcing term, which is again local. Both of these are local effects. We've only changed it locally. But what's important and how this is actually going to work is that this effect changes our incompressibility condition. So our incompressible flow condition is that this velocity should be incompressible. And when we substitute this into our divergence-free constraint, we end up with a Poisson equation that's got a variable coefficient. It's not just 1 anymore. We've got 1 minus this delta, or again, in terms of this, it's the 0 kernel moment. And this is enough. This lets us use the fact that we're solving for the pressure to get our exact solution everywhere. So you can solve this equation analytically. You end up with a pressure field that looks like this one. So it's got a continuous negative derivative, which is equal to the velocity. And then there's a jump across here. So that's the heaviside function, which resets. And the amount of jump you need is not known ahead of time. Yeah, so it depends on your domain. In this case, it depends on the length of this pipe. But the pressure solver will happily do that for you. That's what pressure solvers are happy to do. You really need to have this variable coefficient equation. Once you plug that into the governing equation up here, you get exactly the solution you want, even though we've only added forcing right on the body. All right. Oh, so back to Hans' question. So Hans' question was, how can we deal with these coefficients? So if we look at this again, kind of using the notation of this mu0 is 0 inside the body. How are we going to handle that is the question. That's not a bug, actually. This is completely mandatory. This is what's enforcing the pressure boundary condition. And that's why this code actually works instead of kind of the other sorts of direct forcing and other immersed boundary methods. It also enables the pressure discontinuity. The fact that we turn this off in terms of the momentum equation means that we can have pressures with a giant jump across a small interface, and we don't get some giant force applied to the fluid there. We don't want a giant force. We want there to be the right amount of force on one side and the right amount of force on the other side. And then we want the boundary condition for the velocity to take over inside the body. So this isn't a bug, it's a feature. And it doesn't really matter in terms of the solver. So there's a lot of solvers that can handle these zeroed coefficients. Two that we've used are a Krylov solver. So specifically, this is going to give us a symmetric matrix. So we can use a preconditioned conjugate gradient solver. But it's even better to use geometric multigrid. And the reason why is because it takes advantage of the Cartesian structure of the grid. So since we're being handed this nice structure, we should use it. We can quantify how well that worked. So we've got a disk accelerated from rest here as a good example case. So this is sort of the 3D version, I guess, of that piston case. Now we're not stuck in a little pipe though. So this is in an infinite domain and we accelerate a disk from rest. This is just a quarter of the simulation domain. You can see that as you accelerate, you generate these cool vortical structures. The added mass for this is known from potential flow. The coefficient should be 1/3. And there have been measurements of the peak experimental drag, kind of by David Rival's group, published in JFM. And again, in Marin's paper last year, he showed that we can get these kind of forces almost perfectly. So this green line are 3 resolutions of the BDIM approach, his particular BDIM approach, which works extra well for super thin geometries called BDIM sigma. And no matter how well you're resolving the thickness of that, you end up with essentially the same solution, which makes sense because we're going normal to the flow. It shouldn't really matter how well we're resolving the thickness, as long as we're satisfying our pressure and velocity boundary conditions. We get essentially the same thing. You can see that we get the initial force, that's the from the potential flow solution, and we also get the correct experimental peak. On the other hand, if you're using like a direct forcing method, you totally miss that initial thing because again, they're not correcting the Poisson equation. And then they also end up overestimating the peak force. And this solution depends a lot on the Reynolds number, unfortunately, as well. So go ahead and read Marin's paper for some more details on that. He's also giving a cool presentation in Eurodyne this year. So here's a number of situations where we've got kind of least flexible inverted flag to the most flexible inverted flag. And he'll talk about how he coupled the FEA solver to the flow solver, but just using one of his plots to help validate that once you get the forces right, then you can get the dynamics right. It's a requirement, obviously. So there's been, again, some JFM work that's been done on this, and you transition between that kind of fixed plate to a high amplitude to being just kind of stuck and fluttering at the bottom. And we're getting all of those transitions just right in terms of tip deflection as a function of flexibility. All right, cool. So that's about as much of a deep dive, I hope, as into that as you wanted. And I'll still have time to talk about the particular tool that we're using, which is Waterlily.jl. It doesn't look like I'll have time to talk about data-driven multi-grid, but that's okay. I've given a talk on that before. So Waterlily.jl is a simple and general Julia fluid simulator. So this is the Julia logo here that we're calculating the flow on top of, or here's kind of a dynamic version of Marin's test case, where instead of just accelerating plate, we're doing an oscillating plate. And this solver, written totally in Julia 100%, is very, very fast. So this is one of the two main benchmarks. This is all going into a para CFD conference later in the summer. So this is the Taylor Green benchmark. This video here is 50 million degrees of freedom. And it's run on this laptop that I've got here. It took 30 minutes to run this whole video and to render it. And this is just running on kind of my laptop NVIDIA card. And Bernat, hot off the presses, just tried it yesterday and found that it's 3 nanoseconds per iteration per degree of freedom on one of your very, very big GPUs, I have to imagine, that managed to go that fast. And he reports to me that that's 5 times faster than the kind of spectral solver that you guys have. Of course, that's comparing apples to oranges because Waterlily is not a spectral solver, but it gives you an indication that this isn't just a toy. We're doing stuff that's really very fast. As another example, we've got this kind of donut test case. So this is a recording of me doing a live demo of this that I put up on Twitter last week or so. And you can see that this is a live visualization using Mackie. It's one of Julia's kind of visualization tools. So I can run this on my laptop and I can see the flow evolving as it goes. I could replace that donut with the disk and replicate Marin's case. I could wash it around and get that kind of jellyfish simulation I showed you at the beginning. It's really nice to have something where you can do live visualizations of these kind of immersed body flows. Again, you can see that the code is really nice and short. It's not complicated to set up or run these sort of simulations. And we benchmarked it, and porting this onto GPUs gave us 182x speed up compared to running on a serial CPU. So it scales quite nicely on the GPU. All right, so when ever we talk about this, somebody always says, why Julia? I think Bernat posted a blog post yesterday about this kind of porting situation, and the first question in the comments was, why Julia? Why would you do that there instead of somewhere else? So the reason why is kind of first and foremost, it was the 2-language problem. So Bernat talked about his PhD with me. This is one of the cool figures from that PhD and the resulting JCP paper, where we were kind of learning how to do 2D turbulence models. So the top video here is the flow on a circular cylinder that's been calculated in 3D and then span-wise averaged afterward. And the bottom one is from machine learning convolutional neural net. And it's learning to replicate this kind of 2D turbulence model from the data we generated. But it was a giant pain for not to talk to you about it, because we were using a Fortran solver, which is great and fast, and that's wonderful. But then everything has to be ported over to something that can do machine learning, which Fortran is not set up super well for. I know there's people working on that, and that's great. But at the time we were doing it, and even still, it's a lot easier to do that kind of thing in, say, Python, which is what Bernat did. And then you have to send the data back and forth to run new simulations. So you do one time step in Fortran, and you do a socket to carry it over to Python, which updates the CNN, and then it goes back. Such a pain. And it ends up being more kind of plumbing than science. And the whole point of this was to get rid of the numerics and the plumbing so that you can do the cool work that you want to do. And switching over to Julia hopefully enables that kind of stuff. And it helps because there's not only is Julia very fast, but it's got all this development. So we've got a big scientific machine learning kind of group with Chris Rakakis. There's a lot of people working on cool linear algebra solvers. There's cool visualization tools. I showed you that 3D Mackie stuff. There's a ton of automatic differentiation tools. Diff is the one that we've used before, but there's Enzyme and all kinds of other cool AD stuff built in. And the one that let us do the porting was kernel abstractions. So these kind of things you don't have to do yourself then, right? My expertise is in fluid mechanics, and I'm really happy to let somebody else deal with this other stuff as much as possible. So very quickly, I wanted to talk about the kind of guts. So I showed you in that little quick demo of 10 lines for the jellyfish that the final output is a simulation in Julia. So what is this thing, and why is this a nice way to do it? So all we're doing is solving the Navier-Stokes equations. As we said, we're using simple Cartesian-grid arrays for the pressure and velocity and all the other things we need, like we said before. One really cool feature of Julia specifically is that it has this neat multidimensional capability using Cartesian index. So what this lets us do is write the code one time, and it can run in any number of dimensions that we happen to be wanting to do. Sure, fluid mechanics is typically only 2D or 3D, but it's still nice not to have a bunch of code repetition and situations where you might make mistakes and bug everything up. So as a really simple example, we can write a little kind of unit vector sort of thing. So this is a little delta function that takes a step in one direction. And you just tell it what direction you want to step in, J, and it'll adjust the Cartesian index that way. And we can use that to define in one line a really simple finite difference. So say we have the velocity. We want to take the velocity at some step J and subtract the velocity at the original place I. And that is a super easy way to take a finite difference. So we get this whole kind of vector array of all the differences we need with one line of code. And that works in 2D and in 3D, no problem. So here's an example of using that to get the lambda 2 vortex criteria. And again, I don't have to code all of this stuff. So like eigenvalues, it's in there. So really easily, I can just kind of calculate the full matrix of derivatives. I can take the symmetric and anti-symmetric part and plug it into the equation for the lambda 2 and spit it out. And this is so clean and nice, and it makes it really easy to write bug-free code. So that's wonderful. This Cartesian index stuff is also part of the reason why the whole solver is under 800 lines of code. So like that's kind of ridiculous for such a high performance tool. Oops. So I talked a little bit about multigrid, and that is what we use in this code as well. So geometric multigrid, it's a really good choice for this kind of problem, again, because we have this really structured grid. So we have a very simple setup so that we can go down to a coarser grid and down again and then back up. And this kind of V cycle thing is exactly what we do. This gives us order in scaling. So that's even better than kind of a Krylov solver or an FFT. It's sort of optimum. And that's not easy to do, right? Solving variable coefficient Poisson equations can be very tricky, but actually a geometric multigrid solver makes this extremely efficient. And again, it's super clean and multidimensional. So in terms of what we do for Julia, all I have to do is define one function called near, which tells me all the points near some index I. So it returns Cartesian indices, like a little kind of set of points. So I pass in some index I, and it returns all the points near that. So I pass in one point here, and it says, take all of these, and that'll be the answer. So for restrict, it's just a sum over the nearby points. And then how do I go back up? I just take the value there, and I copy it. So I prolongate, setting all the values equal to the values that are near them. That's it. Like, this is essentially the meat of the entire multigrid solver in a couple lines of code. So that's really great. Cool. Last thing I wanted to talk about, well, I guess two more things, is the geometry. So how in particular, I maybe didn't say it long enough, but the nice thing about the BDIM approach is that the momentum equation is still a very simple algebra update for the, like, it's just adding some coefficients. There's no real additional difficulty in the momentum equation itself. The only thing is that you do need to get kind of the body velocity. You need to know where you are relative to the body so that you can get the kernel moments and things like that. So what we do for this is we've defined something called an auto body, which is using automatic differentiation to get all of the stuff we need based on a signed distance function. And the people who have thought about this sort of thing have a bunch of really cool ways of dealing with signed distance functions. So I recommend this website. It's awesome in terms of like doing cool renders based purely on SDFs. And he has a lot of cool test cases that I steal and then run simulations on in terms of, here's a bunch of cubes. What does the flow look like on a bunch of cubes? It's kind of a one-liner in his code and now also in Waterlily. So how that works is we pass in any kind of SDF that we want. So as long as it's a function of space and time, we can evaluate it at every point in the grid. And then that's used in terms of getting kind of this Hessian. So I can take the automatic differentiation, the forward diff package, take the Hessian of the SDF. That gets me all of the gradients, which I need to get the normals. And it gives me the curvatures. So if you want to have accurate forces, you can correct for the curvature of the body, which is really cool. To do motion and get the velocity, we have a mapping function. So we just take whatever the coordinate is that you're actually at, and we map to some other, and we can move that in time. So the jellyfish example, most of the code was actually just defining this coordinate map, which I kind of oscillated the shape of the thing in time. And then to get the velocities, I don't have to define any more functions. I just take the time derivative of that map. That's it. That's our velocity field. So it's really good. Again, it helps you write 10 lines of code and have only about 800 lines for your solver and still do really general stuff. All right. And then finally, a teaser about the GPU. So the short answer for how we ported this to GPU was kernelabstractions.jl. That's a really cool package that was developed to help do high-level abstractions so that we don't have to think about all of the small CUDA-related functions or AMD-related functions. It's all at a much higher level. And also it doesn't just do GPU, it does multi-threading CPU. So all of the threads on your laptop, that all does too. And all we had to do was rewrite one loop function. Now, there were a lot of extra additional things that had to be done so that that one loop function would work. I don't want to oversell it. It was a good week of effort, more like a week and a half maybe of effort. But at the end of the day, the kind of major change was that every time we loop over points, we use a macro in Julia, and that kind of automates that whole process. And if you want to see a more detailed explanation of what's going on there, Bernat just posted this blog post yesterday about kind of a cool example of, I think he used a divergence equation. and showed how that works. And we basically used exactly the same approach to get that 182 times speed up super fast code. All right, so that's it. Sorry, looks like I over-prepared. I have used this code to do some cool stuff like data-driven geometric multigrid, tying together sort of the implementation with the pressure Poisson equation, but we're out of time. So with that, I'll stop the presentation and I'm happy to take any questions.